Hello everyone, welcome back. The last thing we need to talk about in section 15.7 are triple integrals in spherical coordinates. And the first thing we're going to deal with is what is the Jacobian in spherical coordinates, or what do you have to multiply by your function when you switch to spherical coordinates. So in spherical coordinates, dv is represented by rho squared sine phi, d rho, d theta, d phi. So that means when you switch to spherical coordinates, you must multiply your function by rho squared sine phi. So that means if you have some function that you want to integrate over a region E, that function's in Cartesian coordinates x, y, z, you have to replace x with rho sine phi cosine theta, replace y with rho sine phi sine theta, replace z with rho cosine phi, and also multiply your function by rho squared sine phi. So that seems like a lot. And in some cases, it will be. But I'd like to take a few minutes to somewhat derive where this rho squared sine phi comes from. This isn't going to be entirely rigorous, but it'll give you an idea of why it shows up. So imagine that we've partitioned space, so 3 dimensions, into a bunch of spheres, and then I partition each of the spheres. So what I want to do, similar to the cases where we look at areas of different things for double integrals, I want to look at a volume of what I'm going to call a spherical cube. So just pick a region in space that is trapped between 2 spheres, and then those 2 spheres are, the distance between those 2 spheres is chopped up, so I just get this little spherical cube. And we're going to derive a way to find talk about a way to find the volume. So if I have these 2 spheres, I'm going to call the distance, or the radius, of this inner sphere rho, and then this length is going to be my delta rho, or the change in rho between the 2 spheres. So this is going to be one of the values for my volume, and it's going to be the easiest one, right? This is, I think, relatively simple to see. I'm just changing my radius inside this cube, so that's my delta rho. The other 2 are a little more complicated, and so instead of talking about the spherical cube itself, I'm going to talk about this kind of sector leading up to the spherical cube. And I've drawn that over here. And now looking at this, I've drawn all of these arcs incorrectly. These arcs should be facing the other direction. But I'm not going to fix that now. Okay, we'll just deal with this. So this is this dotted piece over here leading up to my spherical cube. So what would be here, I haven't drawn, is the spherical cube itself that I want to find the volume of. So let's say that I have the z-axis here. This, I'm going to call it a sector, is at a fixed angle with the z-axis. The top of it is at an angle of phi. Then between the top and the bottom is the change in phi, so I'm going to call that delta phi. But if you notice, the closer I get to the origin, the smaller this distance becomes. The further away from the origin, the larger this distance becomes. But the change in the angle is always the same. It's still delta phi. So I don't just want to multiply by delta phi, I want to multiply by some scaled version of delta phi that tells me how far from the origin I am. And this distance along these lines is exactly rho, because this is the radius of this inner sphere. So I have my change in rho, my change in phi I'm going to scale with rho, and so that's going to be rho delta phi. So that's going to be the second side of the spherical cube that I want to multiply to get my volume. The third side, I want to look at the change in theta. And theta is the change of an angle in the xy plane. So I'm going to project this object into the xy plane, and that's what I have here in red, the projection into the xy plane. And this delta theta is the angle between, you can think of the side of this sector closest to me and the side that's furthest away from me. So I have delta theta here. But the same thing with delta phi. If I get closer to the origin, that distance is smaller. As I get further away from the origin, that distance is larger. So I need to know, the angle doesn't change though, so I need to know how to scale this delta theta. And before we get to how we scaled it, I'm just going to look at this object as a right triangle. And to look at this a little more simply, I've drawn it again over here. So here's my z-axis. Here is this line segment that represents the radius of the sphere, so it's length rho. And then I'm going to make a right triangle. Now this side of the right triangle is parallel to my z-axis. So I have parallel lines with a transversal, which means, going back to geometry, if this angle is phi, this angle is also phi. Rho is the length of the hypotenuse of my right triangle, so I can use trig to say that this side of my triangle is rho cosine phi, and this side of my triangle is rho sine phi. But this is the length that I care about, because this is the projection of the radius into the xy plane, meaning that this length right here is rho sine phi. So I'm scaling this delta theta by rho sine phi. And so then I can approximate the volume of this spherical cube by delta rho, my change in the radius, rho times delta phi, which is a scaled version of the change in phi, and rho sine phi delta theta, which is a scaled version of the change in theta. And now, if I let all of these things become infinitesimally small, delta rho, delta phi, delta theta become d rho, d phi, d theta, and I'm left with rho times rho sine phi, so I get this rho squared sine phi. Again, this argument isn't entirely rigorous, but it's just to give you an idea of where this comes from, an explanation of how could this come about. So the important thing is, in the spherical coordinates, once you've converted x, y, and z to spherical coordinates, which is what I did here, using those equations from the first video, you also need to multiply your function by rho squared sine phi. Now let's take a look at a couple of examples. So the first example says integrate cosine of x squared plus y squared plus z squared to the 3/2 over the solid, the unit ball. So the unit ball is just the solid where rho goes from 0 to 1, phi goes from 0 to pi, and theta goes from 0 to 2 pi. So it's just the solid centered at the origin bounded by a sphere of radius 1. It's the interior of that. That's the unit ball. So our bounds of integration are given to us. All we've got to do is make sure we convert this to spherical coordinates and make sure we multiply by rho squared sine phi. So that's what I'm doing here. In spherical coordinates, x squared plus y squared plus z squared is rho squared. So I replace that entire thing with rho squared. And then I'm going to simplify this to be rho cubed. And then I need to make sure I multiply by rho squared sine phi. That's part of my dv. That's the Jacobian I have to multiply my function by. And now I'm ready to integrate. And if you notice, we can separate this integral. I have a function of rho, which is rho squared times cosine of rho cubed. I have a function of phi, sine phi, and I have a function of theta, you can just think of 1, all multiplied together. And my bounds are just numbers. So I can completely separate this integral, which is what I'm going to do. Remember, you don't have to do this, but in this case I can. It's going to make it a little simpler, so that's what I'm going to do. So I just get this integral in theta, that's going to be 2 pi. I'm integrating sine with respect to phi, and I have this rho squared cosine rho cubed, which I'm going to use a u substitution to integrate. So u is going to be rho cubed, my du is 3 rho squared d rho, so I'm just missing a 3 here. So then when I integrate, the first integral is just 2 pi. The second integral, I integrate sine to get negative cosine, and then I need to evaluate. And the third integral, you can think I multiply by 3, leave a 1/3 outside, that's where this 1/3 comes from. And then I'm ready to integrate cosine to get sine of rho cubed. And I need to plug in my bounds. When I plug in my bounds, this is what I get. Cosine of pi is -1, so that becomes +1. Cosine of 0 is 1, so I'm subtracting minus cosine, that becomes plus. And cosine of 0 is 1, so this just becomes 2. I plug in 1, I just get 1/3 sine of 1, I plug in 0, minus 1/3 sine of 0, which is 0, so that disappears. And I just get 4 pi over 3 times sine of 1. And that's my answer. Alright, let's take a look at another example. Use spherical coordinates to find the volume of the solid bounded below by z equals the square root of x squared plus y squared, and bounded above by x squared plus y squared plus z squared equals 4. So first, what are these objects? This is a cone, and this is a sphere. So we talked about at least this specific cone in the first video of section 15.7. We'll go through it again. This is in general what the object's going to look like. It's bounded below by a cone, bounded above by a sphere. I also have this in Mathematica. We'll take a look at it real quick. Here it is, bounded below by a cone, bounded above by a sphere. And we need to come up with the bounds of integration for this object ourselves. In order to do that, I'm going to take a look at the equations for each of these objects. So let's go back to the notes. In spherical coordinates, this sphere is just rho equals 2, so it's a sphere of radius 2. And the cone is just phi equals pi over 4. We talked about this in the first video for section 15.7, but if you're not sure, we can use this equation, phi equals arc cosine of z over the square root of x squared plus y squared plus z squared. And since we're concerned about the equation for the cone right now, z equals the square root of x squared plus y squared. So I can substitute square root of x squared plus y squared for z. So the numerator, I just get square root of x squared plus y squared, and the denominator for z squared, I get the square root of x squared plus y squared, which is just going to be x squared plus y squared. I can put if the numerator and denominator are both under the square root, I can just take the square root of the fraction. And so I get x squared plus y squared over 2 times x squared plus y squared. That's just 1 over the square root of 2. And that is the same as square root of 2 over 2. So cosine of what angle gives you square root of 2 over 2? That's pi over 4. So that's another way you can derive that cone is pi over 4. So now if I want to describe this region, first of all, my theta bounds, I'm going around the entire xy plane. I'm rotating all the way around. So theta goes from 0 to 2 pi. Rho goes from the origin up to the sphere. So rho goes from 0 to 2. And phi, I'm centered at the z-axis. So if I start here and I go down, I stop when I get to the cone. So phi goes from 0 to pi over 4. And those are the bounds of my region. I set up my integral. It's a volume integral, so I'm just integrating dv. But in spherical coordinates, dv is rho squared sine phi. So volume in spherical coordinates, you have to integrate rho squared sine phi. I'm going to separate this integral again into a theta integral times a phi integral times a rho integral. And the theta integral is just integrating 1, because I don't have any thetas here. The phi integral is integrating sine phi, and the rho integral is integrating rho squared. So this first integral, I get 2 pi. I integrate sine to get negative cosine. Rho squared integrates to 1/3 rho cubed. I plug in my bounds, and I get that 8 pi over 3 times 2 minus root 2 is the volume of this object. Okay, so that's integrals, triple integrals in cylindrical and spherical coordinates. Make sure you practice these. I've only done a couple of examples. You really need to get comfortable with finding bounds and converting different coordinate systems. And after this, we're finished with chapter 15 for this class, and we'll move on to chapter 16, or what's left of chapter 16.